Hello, and welcome to this OpenTopography tutorial. My name is Chelsea Scott, and in this video, I will be talking about point count and point density for Lidar data. So to begin, what is point count? So here we are looking at the Mississippi River in Minneapolis. And on the left is showing the point count per 25 square meters. So this is the density of the LiDAR data, essentially how many returns we have of the LiDAR data per 25 square meters. And it's plotted on this blue to yellow color scale. The dark blue indicates no returns, and the yellow indicates roughly 14,500 returns, again, per 25 square meters. And what we see here already is that the point density varies substantially spatially. And in particular, we have very few returns along the Mississippi River here, and many more returns here, which corresponds to an area with a lot of trees. So why calculate point count for LiDAR data? So the point count is indicative of the point density. And the point density can vary spatially, as we saw for that Minneapolis example. And with maps of the point count, we can see where the point density is high and also where the point density is low. And some areas will have very low point density. And the digital elevation models that we make are going to be of better quality where the point density is high. So these maps of point density can tell us about the quality of the subsequent digital elevation model that we will make. Second, is we can see where are the flight stripe boundaries and what direction did the airborne LiDAR aircraft fly in. And especially for older data sets, we can have quite substantial artificial offsets between the different flight line stripes. And this will result in quite sharp changes at the boundaries between flight lines. And these boundaries can mimic linear features such as tectonic faults or roads, particularly if you're doing differencing work. And third, changes in point count can indicate a terrain break. For example, as we saw for Minneapolis, there were very few returns in the water, which largely absorbs the laser signal. And there were more returns in the tree canopy because we can get returns within multiple levels of the tree. So in summary, the point count or point density is very useful quality control of your data set, which can then be used to understand the quality of your DEM, as well as potential errors that you will see in the data. So how do I calculate point count? So I'll show you in a second, but we can go to OpenTopography and generate a point count by going to Advanced Services. And then you'll want to look in window number 6, Custom DEM Generation, Local Gridding. And you'll want to click this Calculate Point Count option. So let's look at how to do that on OpenTopography. So here we are at opentopography.org. You'll want to go to Data. And then you can do this calculation for any of our point cloud data sets. So let's go to New Mexico and we'll select this data set, that box. This is a 3-dep data set. We'll click it. New Mexico, southeast. We'll choose a smaller area. You have the option here to click ground or just to do the full point cloud. And if you do the full point cloud, then you get that full density. If you select ground, then the point count will only reflect the ground points. But you want to come then down to Advanced Services DEM generation, local gridding, and then you'll want to say calculate point count. And then here you have gridding parameters. So we have the option of grid resolution, and the default is going to be 1 meter, and that reflects the area that will be used for the calculation. And that area is then given here with the radius value. So if we have a grid resolution of 1, the point count will be calculated over a radius value of 1.4142 meters. And the default option is fine. I do sometimes like to make it bigger, for example, 2, which will give us a little bit more spatial averaging. And then OpenTopography does immediately update that radius value, which we can see there. And then we can come down and submit our job. So in that example, we had selected a grid resolution of 2, which then resulted in a radius value of 2.8. So then we can do some simple math and find out that the point counts that we calculated are going to represent the point count per 25 square meters by just using this area of circle formula. So importantly, it's not the point count per meter squared. Again, for this radius of 2, we're going to be looking at a point count per 25 square meters. And next, I'll show you 2 examples, beginning with the B4 project. This is looking at the Southern San Andreas and San Jacinto faults. This is an older data set that was flown parallel to the San Andreas fault with a point density of 2.98 points per meter squared. So let's look at what the point count looks like. So here we are in QGIS. And here is the topographic hillshade calculated from this data, which you are probably familiar with. And then this is looking at the point count. And first is that we see that the point count varies spatially. So that average value of about 3 points per square meter is not uniform across the area, but we see these quite substantial changes in the point density. Also here, the point density varies along these approximately northwest trending direction, and that reflects the direction that the aircraft was flown in. So to collect the data, the aircraft was flown in a northwest flying direction, and then also a southeast flying direction. And we see quite substantial changes in point density, for example, from here to here. And that sudden change represents a flight line boundary. And it's along these boundaries, particularly for older data sets, such as the B4 data, that we can expect to see these artificial offsets between the data. And so again, they're artificial, so they represent georeferencing errors between the flight lines. They do not represent actual movement along the fault as the aircraft was collecting the data. And when we have these artificial offsets, we should bring some skepticism of either linear features in the topographic hillshade or in differencing results that precisely align with this boundary between the 2 different flight lines. So if you're going to be doing mapping or differencing of this B4 data, it would be really important to have this point count data set out and to make sure that the mapped features don't just align with these changes in the point density. And now we're going to be looking at a Minnesota data. Data set was collected in 2022 and has a point density of 64 points per meter squared. And this is very high. So this is that Minnesota example that we were looking at earlier. And the point density per 25 square meters can vary from approximately 0 to 14,500. And in this case, the most prominent changes that we see in point density depend on the feature at the Earth's surface, with relatively few, but not zero, returns along the Mississippi River. And then the greatest number of returns where there's vegetation, where the laser signal can bounce off different levels of the tree canopy. Just to reiterate that, for example, here we have the Mississippi River, which again has relatively few returns. And then here is the vegetation with more returns. And here's that ground characteristic that leads us to the most profound changes in the point density. But we do see some effect of those flight line stripes. For example, here, this north-south boundary in the point count. And then also here, substantial change in this east-west direction. Thank you for watching. This concludes OpenTopography's video on point count.